Hello viewers, welcome to this class on this course on mathematical finance. You would recall that in the previous class we had talked about the mean and the variance of the returns in case of a portfolio. We have already discussed the case of a two asset portfolio, and then we talked about two scenarios. First, where you seek to obtain the minimum variance portfolio, and secondly we sought to determine what is going to be the minimum variance line corresponding to the minimization of the portfolio variance subject to the constraint that the expected return on the portfolio is kept fixed. So, we will continue this discussion in today's class. So, we begin this lecture with a theorem which will summarize the result that we had obtained in the previous class. So, we assume that the determinant of the covariance matrix of return is not equal to 0. So, that the inverse of C exists, and that the vector of the mean return and u vector, which was the vector of all ones, are linearly independent vectors. Then we can say that a vector of weights W represents a portfolio V on the minimum variance line if and only if this vector W of weights is of the form W is equal to lambda 1 over 2 into vector m into C inverse plus lambda 2 over 2 into vector u C inverse with the Lagrangian multipliers lambda 1 and lambda 2 being given by twice m inverse mu 1 and with mu is equal to mu v. So, now we will move on to a theorem which is known as the two fund theorem, and this will be based on the result that we just stated in case of the minimum variance line, and we will look at an implication of this particular two fund theorem. So, accordingly we state the two fund theorem, and as the name suggests, it will basically involve two different funds. So, under the assumption of the previous theorem, we let the vector W1 and W2 be the weights representing any portfolio V1 and V2 respectively on the minimum variance line. So, that is we are considering two portfolios W1 and W2 with the corresponding portfolios being identified as V1 and V2, and both of them lie on the minimum variance line, but with different expected returns, that is, the expected return mu V1 and the expected return mu V2 for these two portfolios, they are different from each other. Then each portfolio V on the minimum variance line can be obtained as a linear combination of these two. That is, the weight of this vector will be, or the weight of this portfolio will be W, and that will be a linear combination of W1 and W2 for some alpha belonging to R. So, this means that if I consider two portfolios V1 and V2 with the respective expected returns being denoted by mu V1 and mu V2, both of which are different from each other, and these two portfolios lie on the minimum variance line, then any portfolio on the minimum variance line can be written as a linear combination of these portfolios. So, what it means that you are able to actually generate the entire set of portfolios on the minimum variance line by simply taking a linear combination of these two portfolios V1 and V2, provided that they have different expected returns. So, let us look at the proof of this. So, the proof goes as follows. First of all, we find alpha such that mu v is going to be equal to a linear combination of mu v1 and mu v2, which gives you alpha is equal to mu v minus mu v2 divided by mu v1 minus mu v2, and this here, recall that this will exist because mu v1 is not equal to mu v2. So, that means you are able to figure out what is going to be the alpha in terms of mu v1, mu v2 and mu v. So, accordingly, since both the portfolios, remember we chose the portfolios from the minimum variance line. So, since both the portfolios V1 and V2 belong to the minimum variance line, they will satisfy that W1 is going to be equal to mu V1 into a known vector A, that is applicable across all portfolios, plus B, and likewise W2 is going to be mu V2 into vector A plus B. Now, consequently, alpha W1 plus 1 minus alpha W2 2, this is going to be equal to alpha, and I replace W1 with this expression here. So, it will be alpha into mu V1A plus B plus 1 minus alpha, and again I replace W2 with this expression, which will be mu V2A plus B, and this will become alpha mu V1 plus 1 minus alpha mu V2 into A plus vector B, and this is nothing but mu V into A plus B, which is equal to W. So, we have the observation that V belongs to the minimum variance line. So, what I have essentially shown here is that we start off with two portfolios V1 and V2, both of which lie on the minimum variance line, and then I take a linear combination of these two portfolios, resulting in a third portfolio V. So, which means that this portfolio V has the weights given by the linear combination of the weights W1 and W2 of the portfolios V1 and V2 respectively, and it turns out that the weight of this portfolio V can be written as a linear combination of mu V plus A, or rather in the form mu V A plus B. So, which means that this weight W here corresponds to essentially a portfolio that lies on the minimum variance line, where all the portfolios having weights can be written in this particular form. So, now let us look at an implication of this two-fund theorem that we have done. So, I will just note down what the implication for this is. The implication for this is the following, that any portfolio on the minimum variance line can be realized, and by this I mean that you can actually create a portfolio by splitting the available investment amount between just two different portfolios instead of investing in individual assets. So, by this I mean that if I am trying to invest as driven by a minimum variance line, which means that I am seeking to minimize the variance of the portfolio that I will choose while setting my expected return to a certain level, then instead of creating a portfolio of individual assets repeatedly, I would rather go and pick two assets on the minimum variance line, and depending on what the mu v is or what I expect out of this new portfolio, I will decide what is going to be my alpha, and accordingly decide and invest in those two portfolios V1 and V2. So, here the fraction of the amount that I will invest in portfolio V1 and obviously equivalently that I will invest in V2 can easily be figured out, because it is given in terms of mu V, mu V1 and mu V2. So, by this I mean the following. If I go back to this setup, here I have chosen these two portfolios whose expected returns mu V1 and mu V2 are known a priori, and then I decide that I want to create a portfolio with this expected return of mu v, and instead of creating a portfolio of several assets, what I decide to do is that I will choose a value alpha making use of this mu v, and accordingly invest the fraction alpha of my total amount of money in this portfolio V 1 and the remaining fraction of 1 minus alpha in the portfolio V 2, and then the resulting portfolio V that I will get will also be on the minimum variance line, but in this case I have also accomplished the return mu V that I had set my target for. Okay, now we will state the following proposition. And it says the following, that the standard deviation sigma v of a portfolio V comprising of a risky security with expected return mu 1 and standard deviation of returns sigma 1 and a risk free security with return say capital R and standard deviation 0 depends on the weight W1 of the risky security as sigma v is equal to absolute value of W1 into sigma 1. So, this means the following, that I am considering a portfolio V. In my portfolio V, there is a risky security and then there is a risk free security. For the risky security, the expected return is mu 1 and the risk is sigma 1, and for the risk free security the expected return is R, which is just a deterministic quantity because it is risk free, and because it is risk free the standard deviation in this case is going to be equal to 0. And the corresponding weights that I assign to the risky asset and the risky free asset are W1 and 1 minus W1 respectively. Then the standard deviation sigma v of this portfolio comprising of just these two assets, one risky and one risk free, is connected to the standard deviation of the risky asset in the portfolio by this following relation. So, we can write this proof, it is a straightforward proof. So, here obviously sigma 1 is greater than 0, that is the risky asset has a positive risk, and sigma 2 is being equal to 0. Then sigma v square, which is W1 square sigma 1 square plus W2 square sigma 2 square plus twice W1 W2 into sigma 1 2. So, obviously here sigma 2 is equal to 0 and consequently sigma 1 2 is also going to be equal to 0. So, we are only left with the term of W1 square sigma 1 square. So, therefore, sigma v is simply going to be absolute value of W1 into sigma 1 obtained by taking the square root on both sides of this relation. So, then the line on the sigma mu plane is as follows, right, and in this sigma plane means this is for portfolios with one risky and one risk free asset. This will look something like this. This is sigma, this is mu, this is 0 r, which corresponds to the risk free asset or just the investment in the risk free asset. Then this is what the feasible portfolios or all the possible portfolios will look like, and this is basically like a pair of straight lines, as opposed to the parabola that we had seen in case of a portfolio just comprising of the risky asset. And this particular stretch here, this is the region where there is no short selling, right. So, amongst all these portfolios, this particular portfolio 0 r represents just a portfolio which comprises only of the risk free asset, and this portfolio here is a portfolio with no risk free asset, but only just the risky asset. Alright, so this brings me to a very important concept known as the market portfolio, and market portfolio in this framework of Markowitz, or more particularly capital asset pricing model, plays a very important role as some sort of a benchmark index, because it is representative. In principle, it represents the overall behavior of the market as a whole. So, investing in a market portfolio whose weights we are going to derive now is almost synonymous to the situation where you are investing in the market as a whole, with the weights being assigned to each of the assets available in the market being represented by the proportional market capitalization of all those assets. So, this brings us to the next stage of market portfolio, the next topic. So, for the purpose of the discussion from now onwards, so henceforth we will assume that a risk free security is available in addition to n risky securities. So, this means that in the CAPM framework, where we had n risky securities, to this we will now add one risk free security. So, now that you are considering a risk free security, so let us denote the return on the risk free security as R, that you have already seen. So, and in this case the standard deviation is going to be equal to 0, and we will consider the portfolio comprising of a risk free security and either a specific risky security, or if you want to a more generalized setup, a portfolio of risky securities, and I will denote this portfolio as V. So, this means my portfolio V will comprise of a risk free security and then a risky component which can be either in the form of a single risky asset or which will itself be a collection or a portfolio of n number of risky security assets. So, then we take the mean or the expected return of the portfolio as mu v as the return and sigma v greater than 0 as the standard deviation. So, this means that mu v and sigma v are the return and risk for this portfolio, which includes both risky and risk free assets. So, what is going to be the efficient frontier in this particular case? So, as we have seen previously in the theorem, we will draw motivation from there and we will see that in the mu sigma plane, the set of feasible portfolios basically will look something like this, with this particular portfolio here on the y axis denoting a portfolio with only the risk free asset, and this is going to be my sigma v mu v. And here this particular portfolio, which is at the point of tangency of the parabola and this particular line here, this will have a return and risk which are denoted by sigma m mu m, and this is what we will know as the market portfolio. And this top line here, this is what is known as the efficient frontier in case of the portfolio V. So, this essentially what I have got here is the efficient frontier for portfolios which includes a risk free security. So, I will just make a couple of observations here. The area between the two half lines serve as the new set of admissible portfolios which can now also include the risk free security. So, this means that earlier whatever was below this parabola or to the right of parabola, that region was the set of all the feasible portfolios, and now that was the case when you had only the risky assets, and now that we have moved on to a scenario where we can also include a risk free asset, then the shape of the feasible portfolios is such that it includes all the portfolios or the region that is between the two lines, namely this line here and this line here. So, within that region whatever lies is known as the or is the collection of the feasible portfolios, which includes the risk free security also. Now, let us talk about the efficient frontier. Remember that in the previous case we had talked about the efficient frontier after we had defined the feasible set, and the efficient frontier was the top part of the parabola, which represented either the minimum variance portfolio or the portfolio which gives the minimum variance in case of a fixed level of return or gave the maximum return in case of a fixed level of risk. So, likewise we are going to talk about the efficient frontier in case of this portfolio, which includes a risk free asset. So, accordingly we can state the following, that the efficient frontier of this new feasible set is the half line passing through the exclusively risk free portfolio, that is 0 r, and tangent to the hyperbola or the parabola. It looks like a hyperbola or a parabola, representing the minimum variance line constructed from risky securities. So, by this I mean basically that this top part that we have here, this is going to be the efficient frontier, and this is tangent to the hyperbola that was obtained from a portfolio which comprises exclusively of the risky asset. And this particular point of tangency that we have here, this point of tangency is what is known as the market portfolio. So, what purpose does bringing this market portfolio into the picture serve, and how does it actually help us from the investment point of view? So, it helps us in the following way, that if you are a rational investor, so every rational investor who is driven or who respects the dominance relation that we have discussed previously between portfolios, will select their portfolio of choice on this half line, and this half line is called the capital market line, or abbreviated as CML. So, this means that any rational investor who believes in the dominance theory and decides that they want to invest in a portfolio comprising of risky and the risk free asset will then decide to purchase a portfolio from the top half of the line. That means, will decide to purchase a portfolio from here, and this particular half line is what is known as the capital market line, and we will derive the equation of this at a later stage. Now, this particular argument that I have just made will work as long as the risk free return R is not very high. Okay. That is, by very high means that R is less than the expected return of the minimum variance portfolio. So, this market portfolio that we have here, I will denote by M, and then I will make my next statement. The portfolio M corresponding to the point of tangency sigma m mu m is called the market portfolio. So, the next question naturally that we are trying to address or we will look to address is what exactly is this market portfolio, and what are the weights that we are supposed to assign to the market portfolio, and accordingly we will address this next. And the question that you will look at is what are the weights of the market portfolio. So, in order to compute the weights of the market portfolio, we observe that the straight line which passes through the portfolio 0 R, that means the completely risk free portfolio, and the portfolio, the market portfolio sigma m mu m, has the steepest slope or the highest gradient among all the lines through 0 R and sigma v mu v for any portfolio V in the feasible set that we constructed from the risky portfolios. So, by this I mean that you observe that we have this particular line which connects 0 R with some portfolio sigma v mu v. There could be many such possible lines, and you observe that the line which connects 0 R with the market portfolio is going to be that particular line amongst all such lines, and this means that this particular line which connects 0 R and the market portfolio will have the highest slope amongst the innumerable different lines which connect 0 R and sigma v mu v. And so, this is the key factor while we are actually ascertaining what is going to be the weights of the market portfolio M here. So, accordingly, if I just take any line that connects 0 R and any generic portfolio sigma v mu v, then what is going to be the slope of that line? The slope of that particular line is given as follows. The slope of such a line which connects 0 R and sigma v mu v is obviously given by mu v minus R over sigma v minus 0. What is mu v? In the notation, the vector notation that you had used earlier, mu v is going to be W m transpose minus R divided by sigma v, which is square root of vector W C W transpose, where W is the weight of portfolio V. So, W is basically going to be the weight of this particular portfolio in the feasible set of only exclusively risky portfolios. So, please keep that in mind. So, now once I have actually given the slope of the lines joining 0 R and sigma v mu v, and I am trying to find out what is going to be the weight of the market portfolio, and as I mentioned that amongst those lines the market portfolio will be given by that particular line which has the highest slope. So, this motivates us to look at the maximization of this particular slope which connects 0 r with any generic portfolio sigma v mu v. To this end, we then need to find the maximization of this slope W m transpose minus r divided by square root of vector W c W transpose over all vectors W in R n, all weight vectors, such that the constraint W u transpose or sum of all weights being equal to 1 is satisfied. Now, here since we have to actually ascertain the weights and these weights are in R n. So, obviously, we have to resort to the method of Lagrange multipliers as we have used in certain cases previously. So, therefore, we define the Lagrangian f of W into lambda. There is only one Lagrange multiplier, since there is only one constraint, namely sum of weights being equal to 1. This will be given by W m transpose minus r divided by square root of W c W transpose minus lambda into this constraint being included, which is W u transpose minus 1. Now, in order to maximize this, what we do is that we take the gradient and equate it to 0. Alternatively, you can actually open up the entire expression for f of W lambda in terms of the component weights W1 to Wn and take the derivative of f, the partial derivative of f with respect to W1 to Wn and collate them again, and the result will be, and set that equal to 0, and the consequent result would be as follows. The gradient of W of f W lambda, this is going to be square root of W c W transpose minus W m transpose minus r divided by square root of W c W transpose into W c divided by W c W transpose minus lambda u is equal to 0, and which can be written as mu v minus r over sigma v square into vector W c is equal to m minus lambda sigma v into vector u. So, now we have to further simplify this. So, what we do is that we have to figure out what is going to be our lambda. So, accordingly, we will multiply by the vector W transpose on the right and get mu v minus r over sigma v square into W c W transpose is equal to mu v minus lambda sigma v, which implies that lambda is equal to r over sigma v. So, from here we can conclude that therefore, gamma W c is equal to m minus r vector u, where gamma is going to be mu v minus r over sigma v square, so that gamma w is equal to m minus r u into C inverse. Now, here we make an observation. Note that gamma is dependent on w, right. I have the gamma here and this is dependent on w, because you have the term mu v and sigma v square, and so obviously gamma here up to this point is dependent on something that has not yet been ascertained. So, you end up getting some sort of an implicit relation. So, in order to ascertain, to handle this, we have gamma w u transpose is equal to m minus r u C inverse u transpose. So, that means we multiply both sides by u transpose, and what this gives you is the following, that gamma, remember w u transpose is equal to 1. So, this will give you gamma to be equal to m minus r u into C inverse into vector u transpose. So, that means the weight w, so I can now replace the value of gamma here to obtain the weight w to be m minus r u C inverse divided by m minus r u C inverse u transpose. So, now we can sum up the entire discussion as this following theorem. If determinant of C is not equal to 0 and the risk free rate R is lower than the expected return mu MVP of the minimum variance portfolio, then the market portfolio M exists and has weights given by W m vector as m. So, I have already ascertained what my weights are. So, this is given by m minus r vector u C inverse divided by m minus r u C inverse u transpose. So, this is how we actually obtain the market portfolio. Here m is the vector of all the returns, u is the vector of all ones, r is the risk free rate, C is the covariance matrix, and so accordingly all the quantities are known and you can explicitly obtain the weights for the market portfolio. So, this brings us to the end of today's lecture, and in the next class we will look at one of the final topics that we had in portfolio theory, namely the capital asset pricing model CAPM, and some implications of it, especially in the context of the capital market line. Thank you for watching.